So first of all, a random variable, when we're talking about this, number one, has to be a numerical value, okay? And it's a numerical form of the possible outcomes of a given experiment, okay? But again, it has to be a number. Now, you can take different situations and come up with a numerical value to represent things depending on how you interpret the problem. What we are going to be dealing with here is discrete random variables. Okay? Now, what do we mean by a discrete?
Like if it's a random number 1 through 10, it's got to be one of the numbers, an integer, like random integer. It's not going to be all the stuff in between.
Okay, it could be an integer.
It could be anything, really, as long as it's set choices that it has to be.
There we go, good. It has to be set choices. We could have decimals or fractions or something like that, but it has to be a set values, or it's kind of the opposite of continuous, okay? Continuous data, you have all these possible values. And in fact, to try to get an exact value, or really two of the same thing, is virtually impossible. And as we'll see later when we look at the normal distribution, which is a continuous distribution, we actually say the probability of getting any score exactly is 0. Which is kind of an interesting thing to think about. One of the things that you can kind of keep in mind that will help you distinguish between the two is that when we're talking about discrete variables, we're typically talking about things that we can count. All right? So we're counting the number of people with this given characteristic. We're counting, how many of a certain thing fall into this category. When we're talking about a continuous variable, it's something we're measuring, okay? We're measuring the temperature outside, or we're measuring how tall somebody is, or we're measuring how far a car skids after we hit the brakes. All right? Any of those measurements are continuous. Now, we can take some of those situations that have continuous measurements, and by rounding, we can kind of create these discrete variables. Like, for example, if we measured everybody and we just rounded your height to the nearest inch, okay, then it's more like we're counting how many inches tall you are rather than we're actually measuring your exact height, if that makes sense. Because we rounded, we're creating distinctions between the values that make them discrete, okay? Now, some notation you need to be familiar with is pay attention to the difference between the uppercase and the lowercase letters here. When we're talking about discrete random variable x, we'll use a capital X or an uppercase X, okay? Now, if there are n possible outcomes, we refer to each of those outcomes with a lowercase x. Those represent specific values, x sub 1, x sub 2, x sub 3, all the way to x sub n, however many possible outcomes there are. Okay? Now, when we're talking about the probability that this random variable takes on a specific value, this is the notation that you'll see. Okay? The probability that a discrete variable x equals the specific value x is something, depending on the situation. Okay? And really what we're getting into here is what's known as a probability distribution. We're going to look at how the probabilities are distributed across the different possible outcomes. So let's take a look at a quick example here. Okay? You at least need to make sure that you understand the notation and stuff. So we're going to look at an example quickly here, and then we're going to do another example. The other example might be a better one, maybe to copy down. This one's a pretty simple one. When we're tossing two coins, the possible outcomes are two heads, head, 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 tail, tail, head, or tail, tail. Now, none of those are numerical values, okay? But we could take that situation, and if we define it based on x is going to be the number of heads that we see, then we have a numerical value. So our random variable x has three possible values, 0, 1, or 2. No heads, one head, or two heads. And then the probability distribution you can see right here. Okay? The probability that our random variable will equal 0, in other words, we have 0 heads, is 1/4. Okay? And we made a little table. Okay? Here's the 1/4 for the probability that x is 0. Okay? Then we have the probability that we get one head. Well, we got that here or here, so that's 1/2. Okay? And then finally, what's the probability that we get both heads? Well, there we have it. There's only one way to do that out of the 4, so the probability there is 1/4. Okay. Now, you might see this put into a table where one column of the table will have this probability that x equals 0, probability of x equaling 1, probability of x equaling 2, and then in the second column of the table, you'll see the different probabilities listed. Okay? Now, there are a couple of graphs that we can use here as well. The column graph, you guys, let's kind of...
Light nuclear has been cleared. Light nuclear has been cleared.
All right. The column graph is simple. You guys have done stuff like that. That's easy enough. These you may not have seen before, but they're still relatively simple, okay? A spike graph is basically just a scatter plot, but we draw a line straight down to the x-axis from each point. So here we have the probability that x equals 2 is 1/4. So we have this point here at 1/4, and then we draw the line straight down to 2. Okay? We've got that probability of one head is 1/2. Okay, so we've got that point at 1/2, and we draw the line straight down to 1. Okay? And then, likewise, no heads has a probability of 1/4, and we draw it straight down to 0. Okay? That's what's called a spike graph. So again, not super complicated, but what that allows us to do is see, all right, here our probability distribution is symmetrical. Okay? Now, again, this is a really simple situation to handle, but you can see how it's symmetrical in this case. There are a lot of different distributions in statistics, okay? Like I mentioned, we're going to look at the normal distribution and the standard normal. There's the binomial distribution, which we look at a little bit as well with the binomial probability theory. But also, There are things like there's an alpha, there's a chi-squared, there's a beta and a gamma distribution. What are some other distributions? I'm trying to remember. I don't remember. But that whole semester of college was kind of rough in statistics. There were only 2 of us in the class, and the other was a grad student who already had her degree in physics, and was well, because it was a grad level class. I was taking it as an elective. Yeah, that was the better question. I should have been taking something else. I think that was my 5th semester. Or wait, no. No. I think that was my 6th semester, my last semester of regular classes, and then I did a semester of student teaching. So, yeah, that wasn't fun. A little note about college. If you can just test out of an earlier level class, but they're not going to give you credit for it, just take the class. I tested out of my 1st level math class, and all that meant was later on I had to take a harder class. And that was the harder class I ended up taking.
Test out of this humanities stuff.
Some of that. Now, if you CLEP out, you actually can get credit. Or if you take the AP test and you get credits, that's a different thing. I didn't get any credits. That was my problem. So, anyways. Yeah, since about 7th grade.
Really?
Yeah. I had an awesome teacher in 7th. Well, I had her 7th through 11th grade.
The same teacher?
Yeah. I had a teacher. It was at my old school. I went to that school K through 12. The previous math teacher retired after my junior year, and then I had a different teacher my senior year, and they had like 2 teachers in the interim while I was in college. And then by the time I finished, I came back and taught for 10.5 years. But I had kids for 6 years straight. And you guys are thinking, poor kids.
So, that would actually be
fun.
Great, because I had a succession of horrible teachers in middle school.
Yeah.
One good one at the end.
It depends. So.
Yeah, it depends on the teacher.
Yeah.
Amazing or just...
But yeah, she was Mrs. Schaefer. She was an awesome teacher.
Is she married to Mr. Schaefer?
Yes, but not here. He was also a math teacher. So.
What is your wife?
She's a nanny right now.
Aww.
So. All right. Couple of things about these probability distributions, though. There are a few things that we need to make sure that we understand to make sure that we actually have a valid probability distribution, okay? For one thing, think about probabilities themselves. What values can probabilities take?
Percents or fractions of one,
Or
either way.
decimals.
They have to add up to a whole value, 100%, 1.
Okay, the individual ones, their value has to be between what and what?
0 and 1.
0 and 1, okay? So here's the thing, if you ever see what they call a probability distribution, where they have a value that's bigger than 1 or less than 0, then you know it's not a valid probability distribution. Something's wrong here, okay? If they say the probability is a -0.2, or the probability is a 1.5, something's wrong, okay?
Something's wrong. Why would they give you a question that was wrong?
Well, you could make a wrong calculation, and you could come up with that. You could make a wrong calculation on
your answer is
something,
that.
and you could get an answer that's faulty. The other thing Michael mentioned here is that your probability has to add up to 100%. Okay? Notice here, remember we said we have these outcomes, x sub 1, x sub 2, x sub 3, all the way up to x sub n. The probability of each outcome, whatever that is, has to all add up to 1. Okay? If you remember back when we did the binomial probability theorem, okay? Remember we had p plus q to the n. all right, for repeated independent events. And what had to be true about P and Q? Do you remember? No. They had to add up to 1 because they had to be complements of each other. Remember? Like if we had a 70% chance of doing one thing, then the percent chance of not accomplishing that would be 30%. And then let's say we repeated that experiment 50 times. All right, we could use that binomial expansion to figure out the probability of succeeding, let's say, 40 out of 50 times. All right, but notice what's happening here. What's 0.7 plus 0.3?
1.
It's 1. 1 to the 50th power is?
1.
1. The probabilities would all add up to 1. Okay, so if they ever asked you to expand this, all right, it just equals 1.
It'll always equal 1.
It'll always equal 1.
So then why would we do that?
Well, maybe just to be tricky or mean.
Wonderful lesson.
Okay, well that wouldn't be really mean. That would be really nice if you caught it. Okay, but again, the whole principle is this right here. All the probabilities add up to 1. Okay? Now, let's take a look at a quick example, a scenario here. Part of the problem with these is making sure that you identify the proper random variable. Okay? So here we have a situation, a magazine store recorded the number of magazines purchased by its customers in 1 week. 23% purchased 1, 38% purchased 2, 21% purchased 3, 13% purchased 4, and 5% purchased 5. So the first question we need to ask is, what is our random variable?
Number of customers.
You guys agree with that?
Yes. I got you.
What's our random variable? What? Magazines? Okay. Well, can you explain what you mean?
Because the magazines are purchased, so this is our
Okay. So number of customers or number of magazines? What do you guys think?
Okay, the random variable is a number for the possible outcomes of the experiment.
Oh, then yeah, it's the magazines. I figured since we're given. Yeah.
Okay, the number of magazines each customer would buy. All right, so here our random variable, if we let that be x, that's going to be the number of magazines.
It says it's a number form.
So 1,
Purchased.
2, 3, 4, 5.
Well, percents are numbers, but
Yeah, but if they only one variable.
we do only have one random variable, but that variable
Has a lot of value.
has different values. Yeah. So here's where we haven't actually seen one of these, but I mentioned it, the probability table. What you'll do with the probability table, we're going to say the probability that our random variable x has the value 1 is what?
23.
Yeah.
0.2.
Yeah, 23%, 23 out of 100, 0.23, however you want to write that. Okay? What's the probability that our random variable has a value of 2?
0.38.
Okay? 0.38. And yes, this is how you would write the probability table. You'd write this out every time. So 0.21. Probability that it has a value of 4. Okay? and probability that it has a value of 5. Okay? Yes?
If they did purchase 1, 2, 3, 4, 5 magazines, and say it was like 16, 20, like a random number of magazines, would it be X equals however many magazines, or do you still order it like 1, 2, 3, 4, 5? Do you know?
You mean like would we have to account for every value? Or
Yeah, like what is that?
It would be every integer or whole number.
So if it said instead that they purchased 23% purchased 15 magazines, 38% purchased 23 magazines, and it wasn't like consecutive, what would we do for that?
you could, because those are the only values talked about, you could just list those.
And it would be
Okay.
X equals 23, X equals.
Because it gave values for these percents, like if you just change the X values to anything, it still adds up to 100% without there being stuff in the middle. So it would just be those values.
Yeah, so here's the thing. Does this add up to 100%?
Let's find out.
If you add it up, it does equal 1. Okay? So that is correct. But just by reading the problem, the fact that they did not list any data for any values bigger than 5, we can infer from that no one bought 6 or 7 or 8 magazines.
My guess is there was one guy who bought 5 and they had low sales.
Okay? Possibly. Now, what else can we infer from the fact that they're giving us this data? What value might you expect to see?
Something.
Huh?
Everyone bought something.
Okay, everyone bought something.
So
Right,
they're probably omitting data.
Well, are we? Are we omitting data?
So the number of magazines purchased by customers in 1 week. I mean, it does specify purchased by its customers, but you would think probability not would be included for the people who didn't purchase a magazine.
Okay, so here, what this comes down to is this. In statistics, we need to define our terms. And guys, when you're writing your IA, if you're doing a statistics topic, you need to define your terms. Obviously, the store doing this study is defining customer as what?
Purchase.
A purchaser. Not just someone who walks in the door, right? Now, for their purposes, that evidently was what they wanted to do. Could there be any value in considering how many people came in and did not buy anything?
See how many bought things.
Yeah. You know, how many people actually come in here are buying things? You know, we mentioned, 5th period, we mentioned bookstores starting to put coffee shops in their bookstore. You know, like Barnes & Noble and Borders and that.
Orders closed.
Okay?
Rest in peace.
But why did they start doing that? Because a lot of people would come in, they'd grab a book off the shelf, find a nice place to sit and read for a half hour, and then leave not buying anything. Okay? And it's not like they're going to tell people, you know, kick people out of the store just because they're sitting and reading and haven't actually bought anything yet. You don't want to keep people from coming in. So what they did is they started to sell coffee in their bookstores so that, well, they might not buy a book, but if we can charge them $5 for a cup of coffee every time they walk in the door, then after a few times, even though they haven't actually bought the book, they've paid for it anyways and all the coffee that they've drunk. Okay? So that was a way that data like that could have been used. These folks are more concerned with, all right, we realize some people don't buy anything, but the people who do, how much are they buying? And then maybe we can get some kind of an incentive program to where if you buy more all at once, you can get some kind of a discount or something like that. Okay? But that is one thing you would want to check. Is 0 implied by the fact that this does not add up to 100%? Well, in this case, no. All right? It does add up to 100%. So we're not implying that 0 should be the rest or something like that. We wouldn't imply that, oh, the rest must be 6 or higher. We would have to imply that it would be 0. Okay? So now we have the probability distribution using a spike graph. Now, one thing to recognize here, guys, especially later when we look at graphing probability density functions on your calculators, okay, what's the highest any of these graphs will ever go? 1. So when you set your window on your calculator, don't set it going from -10 to +10 on your y-axis. Set it going from like 0 to 1 so you can actually see it. Otherwise, it's just going to look like a horizontal line. You won't be able to see that curve.
Can you do spike graphs on your calculator?
You could do scatter plots on the that's how you would do it on your calculator. Okay? So, here we look at it, the highest it goes is 38%. So I'm going to make the top here be a 0.4, and I'm going to go up by 0.05 each time. So let's see, that'll be 0.2, here's a 0.3, here's a 0.1, here's a 0.05, and there's the halves there as well, okay? So we're going up by 0.05, 5% each mark. And all you would have to do is your random variable will always be your horizontal axis. Okay? So 1, 2, 3, 4, 5, that's always the horizontal axis. And then basically, again, you're just doing a scatter plot and drawing a vertical line straight down to the x-axis. So at 0.23, that's going to be almost up to 0.25, so about right there. And then we just draw it straight down. Okay? 0.38 is almost all the way up to the top. So there's 0.38. Okay? 0.21 would be a little lower than 0.23. Okay, then we had 0.13, just below 0.15.
Pardon the interruption. We are currently under lightning alert.
Thor is back. All right. And then we have 0.05. Okay? So that would be our spike graph for this probability distribution. Okay? Does that make sense? It's pretty simple. So, two main things from this lesson. One is the notation and the different kinds of graphs. The other thing is, from here, making sure that you can identify a valid probability distribution. All the probabilities are between 0 and 1, and all the probabilities add up to 1. Okay? So, I do have a few problems to try, for you to try. Let me stop this.